Hello everyone, my name is Mia Kokic and I'm a PhD student at Robotics Perception and Learning Lab at KTH Stockholm. And today I will talk about my work, Learning for Task-Oriented Grasping. So grasping comes naturally to humans. Even from an early age, it is one of the first reflexes we develop. And as we get older, we are able to produce more complex actions with objects, we develop hand-eye coordination, and ultimately, we become very good at dexterous manipulation. However, the brain plays an important role from the beginning. We are not only good at grasping on a physical level, but we are also very good and creative when it comes to reasoning about how we can use objects for different tasks and how to grasp them for a certain task. The former is closely related to the theory of affordances that I will talk about later, and the latter is known as task-oriented grasping, or TOG. Since there is a strong interplay between different task, object, and grasp variables, the problem was addressed in the past by devising probabilistic networks that allow for an easy inference and that can naturally deal with uncertainty. But on the downside, they rely on manually designed features. With the advent of deep learning, manual features were replaced with convolutional neural networks. However, flexible encoding of different high-dimensional variables and data annotation is still an open problem. In my work, I have explored both of these issues and developed methods that allow robots to reason about objects and tasks they can afford, and how to grasp them given a certain task and a specific embodiment, a gripper. Now I will talk about my work. So our first paper, Affordance Detection for Task-Specific Grasping, addresses the problem of reasoning about object affordances and producing stable, task-compliant grasps on novel objects. Concretely, we developed a method that allows us to automatically infer affordances or parts of objects that are important for a certain task, such as blades for cutting or shafts for screwing, and how we can use those affordances to produce task-oriented grasps. We decouple the problem into two subproblems. First, from an object representation and a task, we infer object features that we use to formulate constraints. And second, we use those constraints with a grasp planner to produce grasps. We consider two constraints, one on hand-object contact regions, and second on approach directions. The first constraint pertains to detecting object affordances, namely blades are used for cutting and the hand should avoid them. And the second pertains to object orientation in space and desirable approach directions for a certain object category, namely knives are grasped from the top when cutting. Ground truth data for training consists of synthetic data sets of objects that are manually segmented into parts labeled with a task and assign nominal approach directions. We train two networks that operate on binary voxel grids to detect these features. During inference, we first detect affordances, orientation, and an object category, formulate constraints, and pass them to an optimization-based grasp planner to execute grasps. We experiment with producing only stable grasps on objects, grasps that satisfy only one constraint, and grasps that satisfy both constraints. So one of the limitations of this work was that it requires decoupling into two subproblems to produce these grasps. Furthermore, an optimization-based grasp planner needs a full 3D model of an object to compute stable task-compliant grasps. So in our second paper, we have developed a unified model, namely one network for predicting stable and task-oriented grasps on novel objects. While the standard approach to learn grasping is to use simulated data or synthetic data, a challenge with simulated data is that certain properties, such as weight distribution, material, and so on, are difficult to simulate, or there is a sim-to-real gap. This is even more exacerbated when grasps are constrained to a specific part and orientation, what is the case with task-oriented grasping. Thus, we augment our model with an online adaptation component that uses Bayesian optimization to refine grasps in the real world to address this sim-to-real gap. Concretely, our method produces two scores given a partial view of a novel object. One is the stability score, and the other is a binary task score that indicates for each possible grasp on an object whether it is suitable or unsuitable for contacting given a task. We can use these scores to execute grasps in the real world and use the output to guide the online adaptation on a specific instance of a known category. To learn the task score, we manually segment objects into parts that are suitable or unsuitable for a task and collect stability scores in a grasping simulator. To make the signal for Bayesian optimization richer, we consider 3 different stability scores and represent a grasp with 4 parameters to make it gripper agnostic. The parameters include grasp position, offset from the surface, gripper orientation, and approaching normal. Our results demonstrate that we can use our method to execute top K stable task-oriented grasps. Furthermore, when a method fails due to certain real-world challenges, Bayesian optimization can improve the results significantly. As stated before, one open problem with task-oriented grasping is that it requires manual annotation of either affordances or parts that are relevant for a certain task. So the data collection is still an open problem. However, the internet is full of images and videos of humans manipulating objects in different scenarios. It would be great if we could use this data to obtain task-relevant annotations for free. The problem, however, is that this data is often 2D, lacking sufficient information such as context and the hand placement for learning to grasp. So in our paper, Learning to Estimate Pose and Shape of Handheld Objects from RGB Images, we approached this challenge by devising a model that lifts this data from 2D to 3D. So the idea is to use state-of-the-art on 3D hand pose estimation from RGB to estimate the hand parameters, and then to develop a convolutional neural network that leverages this information to predict an object pose and shape from RGB. Our intuition is that using the hand facilitates object pose and shape estimation, since these two are often complementary during rigid grasping. So to estimate the pose and shape, we first pre-process the data and obtain hand estimates. Then our HOPSNet, which stands for Hand and Object Pose and Shape, predicts the pose, or position and a rotation matrix, and the shape feature. To finally get a 3D model, we find the most similar looking mesh from the same category by matching an image feature with pre-computed shape features and select the nearest neighbor in the embedding space. The embedding space is generated by training a Siamese network that maps image and shape features of the same object close together in the embedding space and distant if an image and shape belong to different objects. Finally, we import the hand and object into a grasping simulator and refine the poses such as the hand does not protrude the object. To train the network, we use synthetic objects that differ in the appearance from the real-world objects. We make them realistic via image-to-image translation network called augmented cyclogram. Augmented cyclogram translates the appearance of a synthetic object to that of a realistic one, and it is trained on unpaired instances from both domains, one domain being synthetic objects and the other realistic objects from the internet. Our qualitative results show success in estimating poses and shapes of objects. Our quantitative results confirm our hypothesis that using the hand as an additional input can improve object estimates. The main limitation, however, is the dependence on the pre-processing steps, which means that the whole pipeline suffers if the initial hand estimates are wrong. Thus, in our journal paper, Learning TOG from Human Activity Datasets, we improved on this by training our own hand detector on a novel RGB dataset of human hands. Furthermore, as our initial motivation was to process the existing RGB datasets and collect the data for Learning TOG, we demonstrate that we can use our method to first mine the examples from a large RGB human activity dataset, and furthermore, that we can use the data obtained in this way to compute task-oriented graphs. First, we address the problem of hand and object pose and shape estimation, where we build upon our previous work and develop a method that predicts hand and object values from RGB. Concretely, we train a CNN on two datasets, one for hands and another for objects. Hand predictor outputs hand pose and configuration, and object predictor outputs object pose and shape. Like in our previous work, we augmented the object predictor with hand values to facilitate learning and add a Siamese component that generates an embedding space for querying the most similar looking shape to that in the image. We compare our results to state-of-the-art on hand object pose shape estimation qualitatively and quantitatively. A state-of-the-art method reconstructs meshes of hands and objects from an input image. Quantitatively, we achieve better results on a manually labeled subset of our dataset, and qualitatively, our estimates are more precise than the existing method. Finally, we process the whole human activity dataset and train a network that takes as input a partial point cloud and a task, and segments an object into task-suitable regions, or regions that are suitable for contacting given a task. To ensure grasp transfer, we represent a human grasp in terms of an approach direction, offset from the surface, and a gripper roll. Finally, we demonstrate the applicability of our approach on a set of real-world objects with a robot and show that in comparison to the reconstruction method, we achieve better and more realistic results. So in conclusion, we developed the method for detecting object affordances and use them to learn how to grasp for a given task. Furthermore, we developed a unified model for predicting task suitability and graspability on novel objects with online adaptation to address the sim-to-real gap. And finally, we developed a method for predicting hand and object poses and shapes from RGB, which we use to mine a human activity dataset to learn task-oriented grasping without the need for manual labeling. Thank you for your attention.